Hello and welcome to Beyond Earth. I'm really glad you found your way here tonight, settling into this quiet moment where we can journey together through the deepest corridors of time. I'm so glad you're here, wrapped in whatever comfort you've chosen for yourself, whether it's the soft glow of a bedside lamp, the gentle hum of evening settling around your home, or perhaps the peaceful darkness that invites contemplation and wonder. This is a space where we can let our minds drift backward, far beyond the familiar rhythms of human history, beyond the rise and fall of civilizations, beyond even the first stirrings of life itself, to explore a question that has captivated scientists and dreamers alike. What was our planet like in those unimaginable eons before the first spark of life flickered into existence? Tonight, we're going to embark on a journey that will carry us through nearly 2.5 billion years of Earth's earliest history, a time so remote and alien that it might as well be another world entirely, yet it is the very foundation upon which everything we know and love has been built. We'll walk together through landscapes that existed in absolute silence, where no bird ever sang, no insect buzzed, no leaf rustled in an ancient breeze, where the only sounds were the deep, primal voices of the planet itself, the crash of primordial waves against shores of naked rock, the rumble of volcanoes painting the sky with fire and ash, the whisper of winds carrying nothing but dust, and the promise of change across barren continents that knew no footstep, no root, no gentle touch of living things. Oh, and if you're enjoying these stories, I'd really appreciate a like or subscribe. I'm super curious where you're all listening from, so drop a comment with your location and what time it is there. All right. Let's head back to this incredible world that was our Earth, 4.5 billion years ago, when our planet was nothing more than a molten ball of rock and metal spinning through the cosmic darkness. Imagine, if you will, stepping out of time itself and floating high above this primordial Earth, watching as gravity and the fundamental forces of nature slowly, patiently sculpt a world from the chaos of the early solar system. Below you stretches a surface that glows like a coal in a cosmic hearth, where continents are not yet born, and oceans exist only as vast clouds of steam swirling through an atmosphere so thick and poisonous that it would be utterly alien to any life form we know today. This is the Hadean Eon, named after Hades itself, not because it was a place of punishment, but because it was a realm of such intense heat and violence that it seemed like the very antechamber of creation, where the basic elements of our world were being forged in fires that burned hotter than any human imagination could conceive. The story begins, as all the greatest stories do, with violence and beauty intertwined in ways that seem impossible, yet here they were, dancing together in the early solar system, like lovers who destroy each other in order to create something entirely new. Picture the young sun, newly ignited and burning with the fierce intensity of nuclear fusion, sending waves of radiation and solar wind cascading outward through a disk of debris left over from the solar system's formation. A disk filled with chunks of rock and ice and metal that collided and merged and shattered in an endless cosmic ballet that would eventually give birth to the planets we know today. In this maelstrom of creation, Earth was taking shape through a process that scientists call accretion, a word that sounds gentle but describes something far more violent and magnificent than its soft syllables might suggest. Imagine millions upon millions of asteroids and planetesimals, some no larger than mountains, others the size of small moons, all drawn together by the inexorable pull of gravity, smashing into each other with such tremendous force that they melted upon impact, their materials mixing and combining in a growing sphere of molten rock that would eventually become our home. Each collision released energy equivalent to thousands of nuclear bombs, heating the surface to temperatures that would melt copper and bronze, creating a world where the very ground beneath your feet would have been a sea of liquid rock, glowing red and orange and white with heat that could be felt from space. The young Earth spun much faster in those days, completing a full rotation in perhaps 6 hours rather than 24. Which meant that this molten surface was constantly stirring and mixing, like some cosmic soup being stirred by invisible hands, ensuring that the heavy elements like iron and nickel gradually sank toward the center, while lighter materials rose to form what would eventually become the earliest crust. But perhaps the most extraordinary chapter in this early story came when Earth was struck by an object roughly the size of Mars, a collision so monumentally catastrophic that it ranks among the most important single events in the history of our planet. This impact, which scientists have named the giant impact hypothesis, didn't simply leave a crater or cause some local damage. It essentially melted the entire surface of the Earth, vaporizing rock and metal and sending a spray of debris into orbit that would eventually coalesce to form our moon, that gentle companion that now lights our nights and pulls our tides, but was born from an act of destruction so complete that it reset the clock on our planet's development. In the aftermath of this cosmic catastrophe, Earth began the slow process of cooling, and it's here that we encounter one of the most beautiful and mysterious periods in our planet's history, when the first rains began to fall from skies that had been filled with nothing but steam and ash for millions of years. Imagine those first drops of water condensing from clouds of vapor that had circled the globe like a permanent shroud, finally cooling enough to fall as liquid, rather than remaining suspended as gas in the superheated atmosphere. But these weren't gentle spring showers or refreshing summer storms. These were rains that fell continuously for millions of years, perhaps even hundreds of millions of years, creating what some scientists poetically call the long rain, a period when water fell from the sky in an unending deluge that gradually filled the deepest basins and created the first oceans, vast bodies of water that were initially so hot they would have boiled any living thing instantly, yet represented the first step toward creating the conditions that would eventually allow life to emerge. As we drift through these early eons, it's important to understand that the Earth we're imagining is not simply a younger version of the world we know today. It's a fundamentally different planet, operating under different rules, with a different atmosphere, different geology, and a completely different relationship with the space around it. The atmosphere of early Earth contained virtually no oxygen, that life-giving gas that we breathe without thinking, but instead was dominated by carbon dioxide, methane, ammonia, and water vapor, creating a greenhouse effect so intense that even with the sun being significantly dimmer than it is today, surface temperatures remained hot enough to keep water liquid across most of the planet. This early atmosphere was also much denser than what we experience today, perhaps 10 or even 20 times thicker, which meant that the pressure at the surface would have been crushing by our standards, like being hundreds of feet underwater, and the sky would have appeared not the familiar blue we know, but rather a perpetual haze of orange and brown and grey, lit by lightning that flashed almost constantly through the thick, turbulent air. The greenhouse gases trapped heat so effectively that there may have been no ice anywhere on the planet, no polar caps, no frozen mountains, just endless expanses of warm water under cloudy skies that never cleared. Without the protective ozone layer that shields us today, the surface of early Earth was bathed in ultraviolet radiation from the sun, radiation so intense that it would have been lethal to any complex molecules that tried to form. Yet it was this same radiation that may have provided the energy needed to drive the chemical reactions that would eventually lead to the formation of the first organic compounds. It's one of those beautiful paradoxes that seem to define the story of our planet, that the very conditions that would have been instantly fatal to life as we know it may have been essential for creating the chemistry that would eventually make life possible. The landscape of this early Earth was simultaneously more violent and more serene than anything we might imagine, a world where massive volcanic eruptions were as common as rainstorms are today, sending columns of ash and gas dozens of miles into the atmosphere. Yet also a world of such profound silence that the only sounds would have been the deep, geological voices of the planet itself, the rumble of earthquakes, reshaping continents that were still soft and pliable, the crash of waves against shores of black volcanic glass, the whisper of winds carrying nothing but the chemical signatures of a world still learning how to be itself. We must remember, as we explore these ancient landscapes in our imagination, that this was a world utterly without the softening influence of life, without the gentle chemistry that living things bring to their environment, without the oxygen that rusts iron, or the carbon cycles that moderate climate, or the countless tiny organisms that break down rock and create soil. Every surface was naked mineral, every shore was sterile stone, every mountain slope was bare rock weathering under the patient influence of wind and water and time, creating the first sediments, the first layers of sand and clay that would eventually become the pages in Earth's geological history book. Yet even in this apparently barren world, there were processes at work that hint at the incredible creativity and complexity that would eventually emerge. Processes that scientists are only now beginning to understand and appreciate. The chemistry of early Earth was incredibly active and dynamic, with volcanic vents on the ocean floor creating environments where hot, mineral-rich water mixed with cooler seawater, generating gradients of temperature and chemical composition that may have served as natural laboratories for the formation of the first complex organic molecules. In these deep ocean environments, protected from the harsh ultraviolet radiation at the surface, chemical reactions were taking place that would have seemed almost magical to any observer who could have witnessed them. Simple compounds combining and recombining in ways that gradually increased in complexity, creating chains and rings and spirals of atoms that began to exhibit properties that were almost, but not quite, like life itself. As this first chapter of our journey through deep time draws to a close, I invite you to rest for a moment in the contemplation of this incredible world that existed for so long before any of us, before any living thing, gazed upon its wonders. Tonight, we've barely begun to scratch the surface of this amazing story, and in the chapters that follow, we'll explore how this molten, sterile world gradually transformed itself into something that could nurture and sustain the miracle of life. Close your eyes for a moment, if you'd like, and try to imagine yourself standing on the shore of one of those ancient oceans, under skies that have never known the flight of a bird or the drift of a cloud seeded by living processes, breathing air that no lung has ever filtered, feeling the warmth of a world that is still cooling from its fiery birth, still settling into the patterns and rhythms that will eventually create the stable, nurturing environment we call home. In our next chapter, we'll journey deeper into the Archean Eon, that mysterious period when the first stirrings of chemistry began to organize themselves in ways that would eventually cross the threshold from complex chemistry to simple life. And we'll explore how the violent, beautiful world we visited tonight began its transformation into something even more extraordinary. Until then, rest well in the knowledge that you carry within yourself the chemical legacy of these ancient times, that the iron in your blood was forged in the heart of an exploding star, that the water in your body once fell as rain on shores no living eye had ever seen, and that you are, in the most literal sense, made of the same materials that built this incredible planet we've been exploring together. Sleep peacefully, knowing that tomorrow we'll continue this journey through deep time, and that the story we're telling together is not just the story of an ancient Earth, but the story of how we came to be part of this continuing cosmic adventure. Sweet dreams, fellow travelers, and thank you for joining me on Beyond Earth. Welcome back to this quiet space we've created together, where time moves differently and the ancient whispers of our planet can still be heard echoing through the corridors of deep history. As you settle back into this contemplative journey, perhaps you can feel the weight of the previous chapter still resting gently in your thoughts. That image of a molten Earth slowly cooling under alien skies, the long rains falling for millions of years, the first oceans filling with water so hot it would have seemed like liquid fire to any living thing that might have tried to touch it. Tonight, we continue our drift backward through time, but now we find ourselves approaching one of the most mysterious and beautiful periods in Earth's history. A chapter that scientists have named the Archean Eon, from ancient Greek words meaning beginning or origin, though what was beginning here was so subtle, so gradual, and so profound that it would take nearly 2 billion years to fully unfold. This is the story of how chemistry itself began to dream, how simple molecules started to dance together in patterns that would eventually learn to preserve themselves, to grow, to change, and finally to cross that invisible threshold that separates the merely complex from the truly alive. Imagine yourself floating once again above this ancient Earth, but now you're looking down upon a world that has aged perhaps 500 million years since we last visited. A world where the violent bombardment of asteroids has finally begun to subside, where the surface has cooled enough that solid rock can form and persist, where the first permanent continents are beginning to emerge from the global ocean like sleeping giants slowly awakening from dreams of fire and steam. The skies above this world are still alien to our eyes, still thick with carbon dioxide and methane and water vapor, still lit by lightning that flickers almost constantly through clouds that never fully clear. But there's something different now, something more settled and patient about the way this planet moves through space. The Earth of the Archean Eon was a world caught between violence and tranquility, where massive volcanic eruptions still painted the skies with ash and fire, yet where something approaching stability was beginning to emerge from the chaos of earlier times. The planet's rotation had slowed somewhat, though days were still much shorter than we know them now, perhaps 8 or 10 hours from sunrise to sunrise, which meant that this world experienced a rhythm of light and darkness that was both faster and more intense than anything we might imagine, with the sun rising and setting in rapid succession, while tides moved across the young continents with a restless energy, driven by a moon that hung much closer to Earth than it does today. But it's beneath the surface of those early oceans that the most extraordinary story of this era begins to unfold, in the deep places where volcanic vents release streams of superheated, mineral-rich water into the cooler depths, creating environments that seem almost like the workshops of some cosmic chemist. Places where the basic building blocks of complexity are slowly, patiently being assembled from the simple elements that make up seawater and volcanic gases. These hydrothermal vents, scattered across the ocean floor like underwater geysers, represent some of the most important and fascinating locations in the history of our planet, because it's here, in these natural laboratories protected from the harsh ultraviolet radiation of the surface, that chemistry first began to explore the possibilities that would eventually lead to life. Picture, if you can, these underwater oases of warmth and chemical activity, rising from the abyssal depths like chimneys made of minerals that crystallize directly from the hot water as it meets the cold ocean, creating fantastic sculptures of sulfur and iron and copper that grow and change and dissolve in patterns that seem almost alive even though they're made of nothing but rock and metal. Around these vents, the water shimmers with heat and swirls with currents that carry dissolved chemicals in concentrations and combinations that exist nowhere else on Earth, creating gradients of temperature and chemistry that serve as natural engines for driving the reactions that build complex molecules from simpler ones. In these environments, something remarkable was happening that we're only now beginning to understand and appreciate fully: the formation of what scientists call protocells. Structures that weren't quite alive but weren't quite just chemistry either. Bubble-like formations that could trap and concentrate certain chemicals while allowing others to pass through their boundaries, creating the first hint of the kind of organized complexity that would eventually become the hallmark of living things. These protocells weren't made of the sophisticated membranes that surround modern cells, but rather of simple films of organic molecules that formed spontaneously when certain compounds came together under the right conditions, creating tiny pockets of concentrated chemistry that could persist for hours or days or even weeks before dissolving back into the surrounding water. What makes these protocells so fascinating is that they represent a kind of bridge between the purely chemical world and the biological world, structures that exhibit some of the properties we associate with life: the ability to maintain their internal environment differently from their surroundings, the capacity to grow and sometimes divide into smaller versions of themselves, the tendency to concentrate certain molecules while excluding others, yet they were still fundamentally chemical rather than biological, still dependent on the specific conditions around hydrothermal vents, rather than being able to create and maintain their own internal conditions. But even more intriguing than the protocells themselves is what was happening inside them, because it's here that we encounter the first hints of what scientists call autocatalysis, a process where certain chemical reactions actually help to create the very molecules that make those same reactions possible, creating self-reinforcing cycles of chemistry that begin to take on a life of their own. Imagine a chemical reaction that not only produces some useful product, but also produces more of the catalyst that makes the reaction happen in the first place, creating a feedback loop that can sustain itself and even grow stronger over time, as long as the basic raw materials continue to be available. These autocatalytic networks, as they're called, represent one of the most important discoveries in our understanding of how life might have emerged from non-life, because they show us how chemistry itself can begin to exhibit some of the properties we associate with living things: the ability to maintain and reproduce patterns of organization, the capacity to evolve and adapt to changing conditions, the tendency to create order and complexity from simpler materials. In the warm, mineral-rich waters around hydrothermal vents, these networks of self-catalyzing reactions could persist for extended periods, gradually becoming more complex and sophisticated as they incorporated new chemical pathways and learned to survive in slightly different conditions. As we drift through this ancient world in our imagination, it's important to understand that what we're witnessing isn't the sudden appearance of life as we know it, but rather the gradual emergence of something that we might call almost life. Chemistry that was beginning to exhibit some of the properties of living things without yet crossing the threshold into true biology. This process didn't happen quickly or dramatically. It unfolded over hundreds of millions of years, with countless experiments in molecular organization succeeding and failing and trying again, each iteration building on the lessons learned from previous attempts, slowly and patiently exploring the space of possibilities that lay between simple chemistry and complex life. During this same period, the surface of the Earth was undergoing its own gradual transformation, as the first solid continents began to emerge from the global ocean, and the processes of weathering and erosion started to create the first soils and sediments. These early land masses were nothing like the green, living landscapes we know today. They were harsh, barren expanses of naked rock, baked under an alien sun and scoured by winds that carried nothing but dust, and the chemical signatures of a world still learning to moderate its own climate. Yet even these sterile landscapes played an important role in the emerging story of complexity, because as rocks weathered and eroded, they released minerals and nutrients into the ocean that would eventually become essential ingredients for the more sophisticated chemistry that was developing around hydrothermal vents. The interaction between land and sea, between the solid earth and the liquid ocean, created cycles of chemistry that began to connect different parts of the planet in ways that hadn't existed during the more violent early period of Earth's history. The atmosphere of the Archean Earth was also slowly beginning to change, though in ways that would have been invisible to any observer watching from space. The constant volcanic activity was still pumping enormous amounts of carbon dioxide and other greenhouse gases into the air, but now there were also the first hints of chemical processes that would eventually begin to modify that atmosphere in fundamental ways. Some of the more sophisticated chemical networks that were developing in and around hydrothermal vents were beginning to produce waste products that included gases like hydrogen, sulfide, and methane, which would rise to the surface and begin to participate in the complex chemistry of the early atmosphere. One of the most intriguing aspects of this period is the possibility that some of these early chemical systems may have begun to develop what we might call primitive metabolisms, ways of using the energy from chemical reactions to drive other chemical reactions, creating the first hint of the kind of energy management that is absolutely essential for all living things. These weren't metabolisms as we understand them in modern biology, but rather simple chemical pathways that could capture energy from one reaction and use it to drive another, more complex reaction, creating the possibility for chemistry to become self-sustaining rather than simply running down toward equilibrium. In the deeper parts of the ocean, where pressure was intense and temperatures were more stable, some of these chemical systems may have begun to develop even more sophisticated properties, including the ability to store information in the form of complex molecules that could serve as templates for creating other molecules with similar structures. This is one of the most crucial steps in the transition from chemistry to biology, because living things are fundamentally information processing systems, entities that can store, reproduce, and modify the molecular instructions that determine their structure and behavior. The molecules that first learned to serve as information storage systems weren't the DNA and RNA that we associate with modern life, but rather simpler compounds that could nonetheless serve as templates for creating copies of themselves, creating the first hint of what we might call primitive heredity. These early information molecules were probably much less stable and much less accurate than their modern counterparts, but they represented a crucial breakthrough in the evolution of complexity because they made it possible for successful chemical innovations to be preserved and passed on to subsequent generations of molecular systems. As we approach the end of this chapter in our journey through deep time, it's worth pausing to appreciate the profound beauty and mystery of what we've been exploring together. Because the story of the Archean Eon is really the story of how the universe first began to dream of life, how chemistry itself started to explore the possibilities that lay beyond mere complexity, towards something approaching true creativity and self-awareness. In the warm, dark waters around those ancient hydrothermal vents, molecules were learning to dance together in patterns that could preserve themselves across time, that could adapt and change and grow in response to their environment, that could begin to exhibit the kind of organized complexity that would eventually give rise to every living thing that has ever existed on our planet. This wasn't a sudden transformation or a dramatic moment of creation, but rather a gradual unfolding that took place over hundreds of millions of years, with countless small innovations and improvements building upon each other in ways that created increasing levels of sophistication and capability. It's a story that reminds us that the most profound changes in the history of our planet often happen slowly and quietly, through the accumulation of tiny steps rather than giant leaps, through the patient exploration of possibilities rather than dramatic breakthroughs. In our next chapter, we'll continue this journey into the deep past, exploring how these early experiments in molecular organization eventually led to the emergence of the first truly living things, and how those primitive life forms began to transform not just the chemistry of the oceans, but the very atmosphere and geology of the entire planet. Until then, rest peacefully in the knowledge that the story we're telling together is your story too, because the chemistry that first learned to dream in those ancient waters flows still in your blood, beats still in your heart, and connects you across billions of years to that first moment when molecules began to imagine the possibility of life. As we return once more to this sacred space of contemplation and wonder, where the boundaries between past and present seem to dissolve like morning mist, I invite you to carry with you the memory of those ancient protocells dancing in the warm waters around hydrothermal vents. Those first tentative experiments in molecular organization that were slowly, patiently learning to preserve patterns of complexity across the flowing river of time. Tonight, we stand at perhaps the most profound threshold in the entire history of our planet, the moment when chemistry finally crossed that invisible boundary and became something entirely new, something that we can recognize, across billions of years of separation, as the first stirrings of life itself. We find ourselves now in the later stages of the Archean Eon, perhaps 3.5 billion years ago, when Earth had settled into rhythms that were becoming increasingly stable and predictable, though still alien beyond our capacity to truly imagine. The planet's surface had cooled enough that vast areas of solid crust could persist for millions of years without being recycled back into the molten interior, creating the first stable platforms upon which the slow work of evolution could begin to build something lasting and cumulative. The oceans had reached a kind of thermal equilibrium, no longer boiling but still much warmer than today, creating conditions that were simultaneously harsh enough to drive complex chemistry and gentle enough to allow delicate molecular structures to persist and reproduce. But perhaps most importantly, the chemical environment of Earth's oceans had evolved to a point where it could support not just the formation of complex organic molecules, but their preservation and replication across multiple generations, creating the possibility for what we might call molecular memory, the ability of chemical systems to remember successful innovations and pass them along to their descendants. This wasn't memory as we understand it in biological terms, but rather a kind of chemical persistence that allowed effective molecular arrangements to be maintained and copied, even as the specific atoms and molecules that made them up were constantly being replaced and renewed. It's in this context that we encounter one of the most beautiful and mysterious chapters in the story of our planet, the emergence of what scientists believe were the first true living cells, organisms so simple and fundamental that they represent the common ancestor of every living thing that has ever existed on Earth. From the smallest bacteria to the largest whales, from the humblest moss to the most complex human brain, these first cells weren't the sophisticated, highly organized structures that we associate with modern life, but rather simple, membrane-bound containers that had somehow learned to maintain their internal chemistry in a state far from equilibrium with their surroundings, creating tiny islands of organized complexity in an ocean that was still dominated by purely chemical processes. Imagine, if you will, floating in the warm, mineral-rich waters of an ancient ocean, perhaps near one of those hydrothermal vents that we explored in our previous chapter. and witnessing the moment when a particularly successful protocell finally made the transition from being merely a complex chemical system to being something that we could genuinely call alive. This wasn't a dramatic transformation that happened in an instant, but rather a gradual accumulation of capabilities that eventually reached a tipping point where the cell could not only maintain itself in the face of environmental challenges, but also create copies of itself that carried forward the essential information needed to repeat the process. What made this transition possible was the development of what scientists call a genetic system, a way of storing the instructions for building and maintaining the cell's essential components in the form of molecular templates that could be copied and passed on to offspring. These first genetic systems weren't based on the familiar DNA that carries genetic information in all modern life forms, but rather on simpler molecules, possibly including RNA or even more primitive chemical structures that could nonetheless serve as templates for creating copies of themselves and directing the assembly of other important molecules. The emergence of these first genetic systems represents one of the most crucial innovations in the history of life, because it solved what scientists call the information storage problem: how to preserve and transmit the molecular knowledge needed to build and maintain complex chemical systems across multiple generations. Without some form of heredity, even the most sophisticated chemical networks would eventually decay and disappear, as their component molecules were broken down and recycled by the environment. But with genetic systems in place, successful innovations could be preserved indefinitely and even improved upon through the gradual accumulation of beneficial changes. But perhaps even more remarkable than the development of genetic systems was the evolution of metabolism, the set of chemical pathways that allowed these first cells to capture energy from their environment and use it to power the reactions needed to maintain themselves and create copies of their essential components. The earliest metabolisms were probably based on chemical reactions that we still see in some of the most primitive organisms on Earth today, processes that extract energy from simple inorganic compounds like hydrogen sulfide or methane or iron minerals, transforming the chemical energy locked up in these substances into forms that could be used to drive the complex biochemistry of living cells. These early metabolic pathways were almost certainly much simpler and less efficient than the sophisticated biochemistry we see in modern organisms, but they represented a crucial breakthrough in the evolution of life because they allowed cells to become energetically self-sufficient, capable of maintaining themselves and reproducing without relying on the specific chemical conditions around hydrothermal vents or other unusual environments. This metabolic independence meant that life could begin to spread beyond its birthplace, near underwater volcanic vents, and explore new environments, adapting to different chemical conditions and eventually colonizing vast areas of the ancient oceans. As these first living cells began to multiply and spread throughout the oceans of the Archean Earth, they started to have an increasingly significant impact on the chemistry of their environment, beginning what would eventually become one of the most profound transformations in the history of our planet. Living cells, even the simplest ones, are incredibly active chemically, constantly taking in nutrients from their surroundings and releasing waste products back into the environment. And when billions or trillions of these cells are all engaged in the same basic activities, the cumulative effect can be enormous. One of the most important ways that early life began to transform Earth's environment was through the production of what we now call biofilms, thin layers of living cells that could coat surfaces on the ocean floor, creating the first biological structures that were large enough to be visible to the naked eye, had there been any eyes to see them. These biofilms weren't just collections of individual cells, but rather communities of organisms that had learned to work together in primitive but effective ways, sharing resources and protection in arrangements that benefited all the participants. The formation of these early biological communities represents another crucial step in the evolution of life on Earth, because it demonstrates that even the simplest organisms were capable of cooperation and communication, albeit in very rudimentary forms. The cells in these biofilms could coordinate their activities to some degree, responding collectively to changes in their environment, and sometimes even engaging in simple forms of chemical communication that allowed them to share information about local conditions or coordinate their response to threats or opportunities. But perhaps the most profound impact of early life on Earth's environment came through what scientists call biogeochemical cycles, the ways that living organisms modify the chemistry of the atmosphere, oceans, and rocks through their metabolic activities. Even the simplest cells produce waste products as they go about the business of maintaining themselves and reproducing. And these waste products often include gases that can escape into the atmosphere, or dissolved chemicals that can alter the chemistry of seawater in significant ways. One of the most important of these early biogeochemical modifications was the production of methane, a powerful greenhouse gas that helped to keep Earth's surface warm despite the fact that the sun was significantly dimmer during the Archean Eon than it is today. Many of the earliest metabolic pathways produced methane as a waste product, and as these methane-producing organisms became more abundant, the concentration of methane in the atmosphere increased dramatically, helping to maintain the relatively warm, humid conditions that were essential for the continued evolution and diversification of early life. At the same time, the metabolic activities of early life were beginning to remove certain chemicals from the environment, particularly dissolved metals like iron that could be toxic to living cells in high concentrations. Some early organisms developed the ability to use these metals as part of their metabolic processes, effectively cleaning them out of the water and depositing them in solid form on the ocean floor, creating the first biological contributions to what would eventually become sedimentary rock formations. These early interactions between life and environment represent the beginning of what we now recognize as one of the most important principles in Earth system science, the idea that life doesn't simply adapt to its environment, but actively modifies that environment in ways that can either support or threaten its own continued existence. This feedback between living organisms and their physical environment would become increasingly important as life became more complex and abundant, eventually leading to transformations of Earth's atmosphere, oceans, and climate that were so profound they can still be detected in the geological record billions of years later. As we drift through this ancient world in our imagination, it's worth pausing to appreciate the profound beauty and mystery of what we're witnessing, because the emergence of the first living cells represents perhaps the most remarkable transformation in the entire history of our planet. In the space of perhaps a few 100 million years, Earth had gone from being a world of purely chemical processes to being a world where chemistry had learned to organize itself in ways that could preserve and reproduce patterns of complexity, creating the first stirrings of the creativity and adaptability that would eventually give rise to all the magnificent diversity of life that we see around us today. These first living cells were still incredibly simple by modern standards, lacking many of the sophisticated features that we associate with even the most primitive organisms alive today, but they possessed the fundamental characteristics that define life: the ability to maintain their internal organization in the face of environmental challenges, the capacity to reproduce and pass on their essential characteristics to their offspring, and the flexibility to adapt and evolve in response to changing conditions. In these basic capabilities, we can recognize the seeds of every biological innovation that would follow, from the development of photosynthesis to the evolution of complex multicellular organisms to the emergence of consciousness itself. The world that these first living cells inhabited was still profoundly alien to our experience, with an atmosphere that would have been toxic to any modern organism and oceans that were much warmer and more chemically active than anything we see today. The continents were still small and barren, covered with volcanic rocks and scoured by winds that carried nothing but dust and the chemical signatures of ongoing geological processes. There were no forests, no grasslands, no coral reefs, no visible signs of life when viewed from space. Just vast expanses of blue-green water under alien skies that flickered with lightning and glowed with the aurora, created by intense solar radiation interacting with Earth's young magnetic field. Yet beneath the surface of those ancient oceans, life was beginning to explore the incredible possibilities that lay ahead, developing new metabolic pathways, experimenting with different forms of cellular organization, and slowly but steadily increasing in complexity and capability. The stage was being set for even more dramatic transformations that would eventually reshape not just the biology of our planet, but its entire physical and chemical character, leading to changes so profound that they would make Earth habitable for the kinds of complex, oxygen-breathing organisms that would eventually include ourselves. In our next chapter, we'll explore one of the most important and transformative periods in Earth's history, when some of these early organisms developed the ability to capture energy directly from sunlight, beginning the process of photosynthesis that would eventually fill the atmosphere with oxygen and set the stage for the evolution of all the complex life forms that we know today. Until then, rest peacefully in the knowledge that you carry within every cell of your body the direct legacy of these ancient pioneers, that the basic biochemistry that keeps you alive and healthy is fundamentally the same as the chemistry that first sparked into existence in those warm, dark waters billions of years ago, connecting you through an unbroken chain of inheritance to the very dawn of life on Earth. Welcome back to this gentle sanctuary of deep time, where we've been traveling together through the most ancient chapters of our planet's story, witnessing the slow transformation of a molten world into something capable of nurturing the first stirrings of life itself. As you settle into this quiet space once more, perhaps you can still feel the presence of those primordial cells we encountered in our last journey, those remarkable pioneers that first learned to maintain themselves as islands of organized complexity in the vast chemical ocean of the early Earth, creating the foundation upon which all future life would build. Tonight, we approach what many scientists consider to be the most revolutionary moment in the entire history of biology, a transformation so profound and far-reaching that it literally changed the color of our planet when viewed from space, altered the chemistry of the atmosphere in ways that can still be measured today, and set in motion a cascade of evolutionary innovations that would eventually make possible every breath you take, every green leaf that captures sunlight in your garden, every complex organism that depends on oxygen for its survival. This is the story of how life learned to eat light itself, transforming the abundant energy of our sun into the chemical fuel that powers the biosphere, beginning a relationship between Earth and its star that has shaped the character of our world for over 3 billion years. We find ourselves now in the middle period of the Archean Eon, perhaps 3 billion years ago, when the early experiments in cellular life had been underway for several 100 million years, enough time for evolution to explore many different approaches to the fundamental challenge that faces every living thing: how to capture enough energy from the environment to maintain the complex chemistry of life while also creating copies of yourself to carry that chemistry forward into the future. The early metabolisms we explored in our previous chapter had been quite successful in their own way, allowing life to spread throughout the ocean basins and establish thriving communities wherever the right chemical conditions could be found. But they were all limited by their dependence on specific chemical resources that existed only in certain locations and could be exhausted if too many organisms tried to use them at once. But somewhere in those ancient oceans, probably in the shallow, sun-warmed waters near the edges of the small continents that were beginning to emerge from the global sea, certain cells began to experiment with a radically different approach to the energy problem, one that would tap into the most abundant energy source in the solar system, the light of the sun itself. This wasn't a sudden breakthrough that happened overnight, but rather a gradual process of molecular innovation that took millions of years to perfect. A cellular machinery that had originally evolved for other purposes was slowly modified and refined until it could capture photons of light and use their energy to drive chemical reactions that would have been impossible under normal conditions. The development of photosynthesis represents one of those moments in Earth's history when a biological innovation was so fundamentally transformative that it changed not just the organisms that possessed it, but the entire planet on which they lived. Unlike the chemical metabolisms that had sustained early life, photosynthesis didn't just extract energy from existing chemical compounds, it actually created new chemical compounds by combining simple, abundant materials like carbon dioxide and water using the energy of sunlight, essentially learning to manufacture food from nothing more than air, water, and light itself. Picture, if you will, one of these early photosynthetic cells floating in the warm, shallow waters of an ancient sea, its simple cellular machinery working to capture individual photons of sunlight as they penetrate down through the water column, each photon carrying just a tiny amount of energy but billions of them arriving every second, creating a steady stream of power that could be harnessed to drive the complex chemistry of life. This wasn't the sophisticated photosynthesis that we see in modern plants and algae, but rather a simpler, more primitive version that produced different waste products and operated under different chemical constraints, Yet it represented the same fundamental breakthrough: the ability to convert light energy into chemical energy that could be stored and used as needed. The early photosynthetic organisms probably looked nothing like the green plants that we associate with photosynthesis today, but were more likely simple, single-celled creatures that might have appeared purple or red or brown to our eyes, their colors determined by the specific light-capturing molecules they used to absorb photons from the sun. These photosynthetic pigments were probably quite different from the chlorophyll that gives modern plants their green color, and they were likely much less efficient at capturing light, but they represented the first biological solution to the challenge of converting solar energy into a form that living cells could use. What made this innovation so revolutionary wasn't just that it provided a new source of energy for the organisms that possessed it, but that it opened up vast new territories for life to explore and colonize. Unlike the chemical metabolisms that were limited to specific environments where the right chemical resources could be found, photosynthesis could potentially work anywhere that sunlight could penetrate, which meant that life could begin to spread into the upper layers of the ocean, into shallow coastal waters, and eventually even onto the land itself, wherever liquid water and sunlight could be found together. But perhaps even more importantly, the waste products of early photosynthesis began to accumulate in the environment in ways that would eventually transform the entire chemistry of Earth's atmosphere and oceans. The specific waste products of the earliest photosynthesis are still debated by scientists, but they likely included various sulfur compounds and organic molecules that began to change the chemical balance of seawater, creating new opportunities for other organisms, while also posing new challenges that would drive further evolutionary innovation. As photosynthetic organisms became more abundant and widespread, they began to form extensive communities in the shallow waters around the edges of continents, creating some of the first large-scale biological structures that would have been visible from space had there been anyone to observe them. These early photosynthetic communities took the form of what scientists call stromatolites, layered structures built by countless generations of simple cells that grew and died and were replaced by their descendants, gradually accumulating into mounds and reefs that could grow to be several meters tall and hundreds of meters across. The stromatolites of the Archean Ocean represent one of the most important and enduring forms of biological architecture in Earth's history, structures so successful and persistent that they continued to be built by microbial communities for billions of years and can still be found growing in certain extreme environments today. These ancient reefs weren't built by any kind of conscious intention or planning, but rather through the simple accumulation of countless individual lives, each cell following its own basic imperative to capture light and reproduce, yet collectively creating structures that provided protection and stability for entire communities of organisms. Walking among these ancient stromatolite reefs, had it been possible, would have been like exploring an alien landscape that was nonetheless unmistakably alive, with surfaces that might have shimmered with the movement of countless microscopic cells, waters that carried the chemical signatures of active photosynthesis, and an atmosphere that was beginning to show the first hints of the profound changes that were to come. The air above these early photosynthetic communities would have been filled with the waste gases of biological activity, creating local environments that were subtly but significantly different from the purely chemical atmosphere that had characterized the earlier Earth. But the most revolutionary aspect of photosynthesis was still to come, because after millions of years of evolutionary experimentation, some organisms developed a more advanced form of photosynthesis that produced a waste product that would eventually transform not just the local environment around photosynthetic communities, but the entire planet. This waste product was oxygen, a gas that was initially toxic to most forms of life, but would eventually become the foundation for entirely new forms of metabolism that were far more efficient than anything that had existed before. The evolution of oxygen-producing photosynthesis represents one of those pivotal moments in Earth's history when a single biological innovation set in motion a chain of consequences that would reshape the entire planet over the course of hundreds of millions of years. The organisms that first developed this advanced form of photosynthesis, probably ancestors of modern cyanobacteria, couldn't have had any way of knowing that their waste product would eventually make possible the evolution of pekprend, complex multicellular life, but their innovation represents one of the most important gifts that one form of life has ever given to all future life on Earth. Initially, the oxygen produced by these early photosynthetic organisms didn't accumulate in the atmosphere because it was immediately consumed by chemical reactions with iron and other metals dissolved in seawater, creating rusty deposits that settled to the ocean floor and can still be found in some of the oldest rock formations on Earth. These banded iron formations, as geologists call them, represent a kind of chemical signature of early photosynthesis, a record written in stone of the first organisms that learned to split water molecules using the energy of sunlight, releasing oxygen as a byproduct of their light harvesting activities. For hundreds of millions of years, this chemical sink was able to absorb all the oxygen that photosynthetic organisms could produce, keeping atmospheric oxygen levels very low and maintaining conditions that were still hospitable to the anaerobic organisms that had dominated early life. But as photosynthetic communities became more extensive and more productive, they eventually began to produce oxygen faster than it could be consumed by chemical reactions, leading to a gradual but inexorable increase in atmospheric oxygen levels that would eventually trigger one of the most dramatic environmental changes in Earth's history. The world that was taking shape during this middle period of the Archean Eon was simultaneously more familiar and more alien than the earlier Earth we've been exploring in previous chapters. It was more familiar because it was beginning to show the first signs of the kind of biological productivity that we associate with living planets, extensive communities of organisms actively modifying their environment, the first large-scale biological structures, the beginning of complex ecological relationships between different forms of life. Yet it was still profoundly alien because the atmosphere contained virtually no oxygen. The dominant life forms were microscopic and unlike anything alive today, and the very process that was beginning to make Earth hospitable for complex life was initially toxic to most of the organisms that existed at the time. The continents of this ancient world were still small and barren, rising from the ocean, as naked volcanic rocks that were slowly being weathered by wind and water, but showed no signs of the biological processes that would eventually create soil and support terrestrial life. The skies were still thick with carbon dioxide and other greenhouse gases, maintaining warm, humid conditions across most of the planet, despite the fact that the sun was still significantly dimmer than it is today. Lightning still flickered almost constantly through the dense atmosphere, and volcanic activity continued to shape the landscape and contribute gases and minerals to the evolving chemical environment. Yet, beneath the surface of those ancient seas, a quiet revolution was underway that would eventually change everything about our planet's relationship with life and energy and chemistry. The simple innovation of photosynthesis, the ability to capture light and use its energy to build complex molecules from simple raw materials, had opened up possibilities that would take hundreds of millions of years to fully explore and develop. But the foundations were being laid for transformations that would eventually make Earth the vibrant, oxygen-rich, biologically diverse world that we know today. As we draw this chapter of our journey to a close, it's worth reflecting on the profound significance of this moment in Earth's history, because the evolution of photosynthesis represents not just a biological innovation, but a fundamental change in the relationship between our planet and the energy that flows from our star. For the first time in Earth's history, life had learned to tap directly into the power source that drives all weather, all climate, all the great cycles of energy that shape our world, creating a direct connection between the biosphere and the cosmos that would eventually make possible the incredible complexity and diversity of life that surrounds us today. In our next chapter, we'll explore how this photosynthetic revolution eventually led to one of the most dramatic environmental catastrophes in Earth's history, an event that scientists call the Great Oxidation Event, when rising oxygen levels triggered a mass extinction that wiped out most of the anaerobic organisms that had dominated early life, while simultaneously creating the conditions that would make possible the evolution of entirely new forms of life that could harness the power of oxygen itself. Until then, rest peacefully knowing that every breath you take connects you directly to those ancient pioneers who first learned to capture sunlight in the warm waters of the Archean Ocean, and that the oxygen that sustains your life is the gift of countless generations of photosynthetic organisms that have been faithfully converting light into life for over 3 billion years. Welcome back to this gentle sanctuary of deep time, where we've been traveling together through the most ancient chapters of our planet's story, witnessing the slow transformation of a molten world into something capable of nurturing the first stirrings of life itself. As you settle into this quiet space once more, perhaps you can still feel the presence of those primordial cells we encountered in our last journey, those remarkable pioneers that first learned to maintain themselves as islands of organized complexity in the vast chemical ocean of the early Earth, creating the foundation upon which all future life would build. Tonight, we approach what many scientists consider to be the most revolutionary moment in the entire history of biology, a transformation so profound and far-reaching that it literally changed the color of our planet when viewed from space, altered the chemistry of the atmosphere in ways that can still be measured today, and set in motion a cascade of evolutionary innovations that would eventually make possible every breath you take, every green leaf that captures sunlight in your garden, every complex organism that depends on oxygen for its survival. This is the story of how life learned to eat light itself, transforming the abundant energy of our sun into the chemical fuel that powers the biosphere, beginning a relationship between Earth and its star that has shaped the character of our world for over 3 billion years. We find ourselves now in the middle period of the Archean Eon, perhaps 3 billion years ago, when the early experiments in cellular life had been underway for several 100 million years, enough time for evolution to explore many different approaches to the fundamental challenge that faces every living thing: how to capture enough energy from the environment to maintain the complex chemistry of life while also creating copies of yourself to carry that chemistry forward into the future. The early metabolisms we explored in our previous chapter had been quite successful in their own way, allowing life to spread throughout the ocean basins and establish thriving communities wherever the right chemical conditions could be found. But they were all limited by their dependence on specific chemical resources that existed only in certain locations and could be exhausted if too many organisms tried to use them at once. But somewhere in those ancient oceans, probably in the shallow, sun-warmed waters near the edges of the small continents that were beginning to emerge from the global sea, certain cells began to experiment with a radically different approach to the energy problem, one that would tap into the most abundant energy source in the solar system, the light of the sun itself. This wasn't a sudden breakthrough that happened overnight, but rather a gradual process of molecular innovation that took millions of years to perfect. A cellular machinery that had originally evolved for other purposes was slowly modified and refined until it could capture photons of light and use their energy to drive chemical reactions that would have been impossible under normal conditions. The development of photosynthesis represents one of those moments in Earth's history when a biological innovation was so fundamentally transformative that it changed not just the organisms that possessed it, but the entire planet on which they lived. Unlike the chemical metabolisms that had sustained early life, photosynthesis didn't just extract energy from existing chemical compounds. It actually created new chemical compounds by combining simple, abundant materials like carbon dioxide and water using the energy of sunlight, essentially learning to manufacture food from nothing more than air, water, and light itself. Picture, if you will, one of these early photosynthetic cells floating in the warm, shallow waters of an ancient sea, its simple cellular machinery working to capture individual photons of sunlight as they penetrate down through the water column, each photon carrying just a tiny amount of energy but billions of them arriving every second, creating a steady stream of power that could be harnessed to drive the complex chemistry of life. This wasn't the sophisticated photosynthesis that we see in modern plants and algae, but rather a simpler, more primitive version that produced different waste products and operated under different chemical constraints. Yet it represented the same fundamental breakthrough: the ability to convert light energy into chemical energy that could be stored and used as needed. The early photosynthetic organisms probably looked nothing like the green plants that we associate with photosynthesis today, but were more likely simple, single-celled creatures that might have appeared purple or red or brown to our eyes, their colors determined by the specific light-capturing molecules they used to absorb photons from the sun. These photosynthetic pigments were probably quite different from the chlorophyll that gives modern plants their green color, and they were likely much less efficient at capturing light, but they represented the first biological solution to the challenge of converting solar energy into a form that living cells could use. What made this innovation so revolutionary wasn't just that it provided a new source of energy for the organisms that possessed it, but that it opened up vast new territories for life to explore and colonize. Unlike the chemical metabolisms that were limited to specific environments where the right chemical resources could be found, photosynthesis could potentially work anywhere that sunlight could penetrate, which meant that life could begin to spread into the upper layers of the ocean, into shallow coastal waters, and eventually even onto the land itself, wherever liquid water and sunlight could be found together. But perhaps even more importantly, the waste products of early photosynthesis began to accumulate in the environment in ways that would eventually transform the entire chemistry of Earth's atmosphere and oceans. The specific waste products of the earliest photosynthesis are still debated by scientists, but they likely included various sulfur compounds and organic molecules that began to change the chemical balance of seawater, creating new opportunities for other organisms, while also posing new challenges that would drive further evolutionary innovation. As photosynthetic organisms became more abundant and widespread, they began to form extensive communities in the shallow waters around the edges of continents, creating some of the first large-scale biological structures that would have been visible from space had there been anyone to observe them. These early photosynthetic communities took the form of what scientists call stromatolites, layered structures built by countless generations of simple cells that grew and died and were replaced by their descendants, gradually accumulating into mounds and reefs that could grow to be several meters tall and hundreds of meters across. The stromatolites of the Archean Ocean represent one of the most important and enduring forms of biological architecture in Earth's history, structures so successful and persistent that they continued to be built by microbial communities for billions of years and can still be found growing in certain extreme environments today. These ancient reefs weren't built by any kind of conscious intention or planning, but rather through the simple accumulation of countless individual lives, each cell following its own basic imperative to capture light and reproduce, yet collectively creating structures that provided protection and stability for entire communities of organisms. Walking among these ancient stromatolite reefs, had it been possible, would have been like exploring an alien landscape that was nonetheless unmistakably alive, with surfaces that might have shimmered with the movement of countless microscopic cells, waters that carried the chemical signatures of active photosynthesis, and an atmosphere that was beginning to show the first hints of the profound changes that were to come. The air above these early photosynthetic communities would have been filled with the waste gases of biological activity, creating local environments that were subtly but significantly different from the purely chemical atmosphere that had characterized the earlier Earth. But the most revolutionary aspect of photosynthesis was still to come, because after millions of years of evolutionary experimentation, some organisms developed a more advanced form of photosynthesis that produced a waste product that would eventually transform not just the local environment around photosynthetic communities, but the entire planet. This waste product was oxygen, a gas that was initially toxic to most forms of life, but would eventually become the foundation for entirely new forms of metabolism that were far more efficient than anything that had existed before. The evolution of oxygen-producing photosynthesis represents one of those pivotal moments in Earth's history when a single biological innovation set in motion a chain of consequences that would reshape the entire planet over the course of hundreds of millions of years. The organisms that first developed this advanced form of photosynthesis, probably ancestors of modern cyanobacteria, couldn't have had any way of knowing that their waste product would eventually make possible the evolution of pekprend, complex multicellular life, but their innovation represents one of the most important gifts that one form of life has ever given to all future life on Earth. Initially, the oxygen produced by these early photosynthetic organisms didn't accumulate in the atmosphere because it was immediately consumed by chemical reactions with iron and other metals dissolved in seawater, creating rusty deposits that settled to the ocean floor and can still be found in some of the oldest rock formations on Earth. These banded iron formations, as geologists call them, represent a kind of chemical signature of early photosynthesis, a record written in stone of the first organisms that learned to split water molecules using the energy of sunlight, releasing oxygen as a byproduct of their light harvesting activities. For hundreds of millions of years, this chemical sink was able to absorb all the oxygen that photosynthetic organisms could produce, keeping atmospheric oxygen levels very low and maintaining conditions that were still hospitable to the anaerobic organisms that had dominated early life. But as photosynthetic communities became more extensive and more productive, they eventually began to produce oxygen faster than it could be consumed by chemical reactions, leading to a gradual but inexorable increase in atmospheric oxygen levels that would eventually trigger one of the most dramatic environmental changes in Earth's history. The world that was taking shape during this middle period of the Archean Eon was simultaneously more familiar and more alien than the earlier Earth we've been exploring in previous chapters. It was more familiar because it was beginning to show the first signs of the kind of biological productivity that we associate with living planets, extensive communities of organisms actively modifying their environment, the first large-scale biological structures, the beginning of complex ecological relationships between different forms of life. Yet it was still profoundly alien because the atmosphere contained virtually no oxygen. The dominant life forms were microscopic and unlike anything alive today, and the very process that was beginning to make Earth hospitable for complex life was initially toxic to most of the organisms that existed at the time. The continents of this ancient world were still small and barren, rising from the ocean, as naked volcanic rocks that were slowly being weathered by wind and water, but showed no signs of the biological processes that would eventually create soil and support terrestrial life. The skies were still thick with carbon dioxide and other greenhouse gases, maintaining warm, humid conditions across most of the planet, despite the fact that the sun was still significantly dimmer than it is today. Lightning still flickered almost constantly through the dense atmosphere, and volcanic activity continued to shape the landscape and contribute gases and minerals to the evolving chemical environment. Yet, beneath the surface of those ancient seas, a quiet revolution was underway that would eventually change everything about our planet's relationship with life and energy and chemistry. The simple innovation of photosynthesis, the ability to capture light and use its energy to build complex molecules from simple raw materials, had opened up possibilities that would take hundreds of millions of years to fully explore and develop. But the foundations were being laid for transformations that would eventually make Earth the vibrant, oxygen-rich, biologically diverse world that we know today. As we draw this chapter of our journey to a close, it's worth reflecting on the profound significance of this moment in Earth's history, because the evolution of photosynthesis represents not just a biological innovation, but a fundamental change in the relationship between our planet and the energy that flows from our star. For the first time in Earth's history, life had learned to tap directly into the power source that drives all weather, all climate, all the great cycles of energy that shape our world, creating a direct connection between the biosphere and the cosmos that would eventually make possible the incredible complexity and diversity of life that surrounds us today. In our next chapter, we'll explore how this photosynthetic revolution eventually led to one of the most dramatic environmental catastrophes in Earth's history, an event that scientists call the Great Oxidation Event, when rising oxygen levels triggered a mass extinction that wiped out most of the anaerobic organisms that had dominated early life, while simultaneously creating the conditions that would make possible the evolution of entirely new forms of life that could harness the power of oxygen itself. Until then, rest peacefully knowing that every breath you take connects you directly to those ancient pioneers who first learned to capture sunlight in the warm waters of the Archean Ocean, and that the oxygen that sustains your life is the gift of countless generations of photosynthetic organisms that have been faithfully converting light into life for over 3 billion years. Welcome back to this quiet haven, where we've been tracing together the magnificent story of our planet's transformation from a molten ball of rock into a world capable of supporting the incredible complexity of life, and now the even more remarkable complexity of minds that can contemplate their own origins across the vast depths of geological time. As you settle into this peaceful space once more, perhaps you can still feel the weight of the previous chapter resting gently in your thoughts. That image of a world transformed by its own success, where the very waste products of life's metabolism became the foundation for entirely new forms of biological possibility, where catastrophe and opportunity dance together in the slow waltz of evolutionary change. Tonight, we enter what many scientists consider to be one of the most mysterious and pivotal periods in the history of life on Earth, a time when the survivors of the Great Oxidation Event began to explore forms of cellular organization that were far more sophisticated than anything that had existed during the first 2 billion years of life's experiment on our planet. This is the story of how simple cells learned to become complex, how individual organisms began to develop intricate internal architectures that could support entirely new levels of biological capability, and how the foundations were laid for every complex life form that would eventually emerge. From the first multicellular organisms to the vast ecosystems of plants and animals that would one day transform the face of the Earth. We find ourselves now in the early Proterozoic eon, perhaps 2 billion years ago, in a world that was still profoundly different from anything we might recognize today, yet was beginning to show the first hints of the biological complexity that would eventually give rise to the rich diversity of life that surrounds us. The atmosphere now contained significant amounts of oxygen for the first time in Earth's history, though still far less than the 21% that we breathe today, creating an environment that was simultaneously more hospitable to certain forms of life and more challenging to others, driving evolutionary innovation in directions that had never been explored before. The oceans of this ancient world were still dominated by microscopic organisms, vast communities of bacteria, and other simple cells that had learned to thrive in the new oxygen-rich environment. But scattered among these familiar forms were the first representatives of an entirely new kind of cellular organization that would eventually revolutionize the very concept of what it meant to be a living organism. These were the first eukaryotic cells, organisms whose internal structure was far more complex and sophisticated than the simple bacterial cells that had dominated life for nearly 2 billion years. Cells that contained specialized internal compartments, intricate molecular machinery, and organizational principles that would become the foundation for all complex life. The evolution of eukaryotic cells represents one of the most important and mysterious transitions in the entire history of biology, a transformation so fundamental that it essentially created a new category of life that operates according to different principles and possibilities than the simpler prokaryotic cells from which it evolved. What makes this transition so remarkable is not just that it happened, but how it happened, through a process that seems almost too extraordinary to be believable, yet is supported by overwhelming evidence from multiple fields of scientific research. The key insight that unlocks the mystery of eukaryotic evolution is the recognition that these complex cells didn't evolve their sophisticated internal structures from scratch, but rather acquired them through a process that scientists call endosymbiosis, a word that means living together inside, describing a relationship where one organism takes up residence inside another organism in a way that benefits both participants. This wasn't a temporary arrangement or a casual association, but rather a permanent merger that was so successful and so transformative that it created entirely new forms of life that were more capable than either participant could have been on their own. Picture, if you will, the moment when this extraordinary partnership first began, perhaps in the warm, oxygen-rich waters of a shallow coastal sea, when a large bacterial cell somehow engulfed a smaller bacterial cell that had evolved the ability to use oxygen for energy metabolism. But instead of digesting this potential meal, the larger cell allowed its captive to remain alive and continue its metabolic activities. This wasn't a conscious decision, of course, but rather a chance event that occurred when the cellular machinery responsible for digestion failed to function properly, leaving the smaller cell intact and metabolically active inside its host. What happened next was one of those beautiful accidents that sometimes drive evolutionary innovation in directions that no one could have predicted, because the smaller cell, now safely protected inside its host, continued to produce energy through aerobic respiration, sharing some of this energy with its host cell in exchange for nutrients and protection from the external environment. This arrangement was so beneficial to both participants that it was strongly favored by natural selection, leading to evolutionary changes that made the partnership increasingly sophisticated and interdependent over millions of years. Eventually, This symbiotic relationship became so intimate and so essential that the two organisms essentially merged into a single, more complex organism, with the smaller cell evolving into what we now call mitochondria, the specialized organelles that serve as the powerhouses of eukaryotic cells, providing the energy needed to support the complex cellular processes that make sophisticated life possible. This transformation was so complete that mitochondria can no longer survive outside their host cells, having given up many of the genes and cellular structures that would be necessary for independent life, while eukaryotic cells have become completely dependent on their mitochondria for the energy needed to maintain their complex internal organization. But the evolution of mitochondria was just the beginning of the endosymbiotic revolution that created eukaryotic cells, because in many lineages, a second symbiotic event occurred when eukaryotic cells that already contained mitochondria engulfed photosynthetic bacteria and established a similar long-term partnership with these light-capturing organisms. Over millions of years, these photosynthetic symbionts evolved into chloroplasts, the specialized organelles that allow plant cells to capture energy directly from sunlight, creating organisms that could combine the energy-producing capabilities of both aerobic respiration and photosynthesis in a single integrated cellular system. The presence of both mitochondria and chloroplasts in the same cell created possibilities for biological innovation that had never existed before, because these organisms could now access energy from multiple sources simultaneously, switching between photosynthesis during the day and respiration at night, or using different energy sources depending on environmental conditions. This metabolic flexibility gave eukaryotic cells tremendous advantages in environments where energy sources were variable or limited, allowing them to thrive in ecological niches that would have been difficult or impossible for simpler organisms to exploit. But perhaps even more important than the acquisition of these energy-producing organelles was the evolution of the complex internal architecture that distinguishes eukaryotic cells from their simpler prokaryotic ancestors. Eukaryotic cells developed sophisticated internal membrane systems that divide the cell into specialized compartments, each designed to carry out specific cellular functions under optimal chemical conditions, creating a level of internal organization that is remarkably similar to the way that complex multicellular organisms organize their tissues and organs. The most prominent of these internal compartments is the nucleus, a membrane-bound structure that houses the cell's genetic material and controls the complex molecular processes involved in gene expression and regulation. The evolution of the nucleus was crucial for the development of complex life, because it allowed eukaryotic cells to manage much larger and more sophisticated genetic systems than had been possible in prokaryotic cells, creating the foundation for the genetic complexity that would eventually make possible the evolution of multicellular organisms with specialized tissues and organs. The internal organization of eukaryotic cells also includes an intricate network of membrane-bound compartments called the endoplasmic reticulum and Golgi apparatus, structures that work together to manufacture, modify, and transport the complex molecules that the cell needs to maintain itself and interact with its environment. These cellular assembly lines are capable of producing proteins and other biomolecules with a precision and sophistication that rivals anything achieved by human manufacturing technology, creating the molecular machinery that makes complex cellular processes possible. Perhaps most remarkably, eukaryotic cells also evolved a dynamic internal skeleton called the cytoskeleton, a network of protein fibers that can be rapidly assembled and disassembled to change the cell's shape, move cellular components around inside the cell, and even propel the entire cell through its environment. This cytoskeletal system gives eukaryotic cells a flexibility and responsiveness that is far beyond anything that simpler cells can achieve, allowing them to respond rapidly to environmental changes and to engage in complex behaviors that require precise coordination of cellular activities. The combination of all these innovations, energy-producing organelles, sophisticated internal organization, complex genetic systems, and dynamic cytoskeletal networks, created a kind of cellular organization that was far more capable and versatile than anything that had existed during the first 2 billion years of life on Earth. Eukaryotic cells could grow larger than prokaryotic cells because their energy-producing organelles could support the metabolic demands of increased size They could develop more complex internal structures because their compartmentalized organization allowed for sophisticated division of labor, and they could engage in more complex behaviors because their advanced molecular machinery could support more sophisticated responses to environmental stimuli. But perhaps the most profound consequence of eukaryotic evolution was that it created the cellular foundation that would eventually make possible the evolution of multicellular organisms, because eukaryotic cells possessed the genetic and metabolic complexity needed to support the kind of cellular specialization and cooperation that multicellular life requires. The internal organization of eukaryotic cells, with their specialized organelles and sophisticated regulatory systems, served as a kind of blueprint for the organization of multicellular organisms with their specialized tissues and complex physiological systems. As eukaryotic cells became more abundant and diverse during the Middle Proterozoic eon, they began to experiment with new forms of behavior and interaction that had never been possible for simpler organisms. Some eukaryotic cells developed the ability to engulf and digest other cells, becoming the first predators and fundamentally changing the ecological dynamics of microbial communities. Others learned to form temporary or permanent associations with other cells, creating the first hints of the cooperative relationships that would eventually evolve into true multicellularity. The world that was taking shape during this period was still dominated by microscopic organisms, and still bore little resemblance to the complex ecosystems that we know today. But it was beginning to show signs of the biological sophistication that would eventually give rise to all the magnificent diversity of complex life. The oceans were filled with increasingly diverse communities of eukaryotic cells, each exploring different strategies for survival and reproduction in the oxygen-rich environment that had emerged from the Great Oxidation event. The continents were still largely barren, showing only the first tentative signs of biological colonization, as hardy microorganisms began to explore the possibilities of life on land. But the foundations were being laid for the eventual evolution of terrestrial ecosystems that would transform the face of the planet. The atmosphere was continuing to evolve as well, with oxygen levels gradually increasing toward their modern values, and the chemistry of the air becoming increasingly suitable for supporting the kinds of complex respiratory processes that would eventually make possible the evolution of large, active, multicellular organisms. As we draw this chapter of our journey to a close, it's worth reflecting on the profound significance of the cellular innovations that we've been exploring together, because the evolution of eukaryotic cells represents one of the most important transitions in the entire history of life on Earth. The complex cellular architecture that emerged during this period didn't just create new forms of microscopic life, it established the fundamental organizational principles that would eventually make possible every complex organism that has ever existed, from the smallest fungi to the largest animals, from the simplest plants to the most sophisticated nervous systems. The mitochondria that power your cells, as you listen to these words, are the direct descendants of those ancient bacterial symbionts that first took up residence inside other cells more than 2 billion years ago. And the sophisticated internal organization of your cells reflects the same basic architectural principles that first evolved during this remarkable period of biological innovation. The very capacity for consciousness and contemplation that allows you to engage with these ideas depends on the complex cellular machinery that first emerged during the Proterozoic eon, when life learned to organize itself in ways that could support the intricate neural processes that make thought and awareness possible. In our next chapter, we'll explore how these sophisticated eukaryotic cells eventually learned to work together in increasingly complex associations, developing the communication systems and cooperative behaviors that would eventually give rise to true multicellular organisms and all the remarkable diversity of complex life that would follow. Until then, rest peacefully in the knowledge that you are, in the most literal sense, a community of ancient partnerships, that every cell in your body contains the legacy of those extraordinary symbiotic relationships that first formed in the ancient oceans of the Proterozoic world, and that the very complexity that makes your existence possible is built upon foundations that were laid during this pivotal period in the history of life on Earth. As we return once more to this tranquil space where time seems to flow differently, where the ancient whispers of our planet's deepest history can still be heard, echoing through the chambers of imagination and understanding, I invite you to carry with you the wonder of those remarkable cellular innovations we explored in our last journey together. Those intricate partnerships between once independent organisms that learned to live and work together so intimately that they became something entirely new, something far more capable and sophisticated than either partner could have achieved alone. Tonight, we witness one of the most beautiful and transformative chapters in the story of life on Earth. The moment when individual cells began to discover the extraordinary possibilities that emerge when cooperation becomes so complete and so essential that separate organisms essentially become different parts of a single, more complex whole. We find ourselves now in the later stages of the Proterozoic eon, perhaps 1.5 billion years ago, in a world where the sophisticated eukaryotic cells we encountered in our previous chapter had been exploring the possibilities of their new cellular architecture for hundreds of millions of years, gradually developing more complex behaviors, more sophisticated chemical communication systems, and more intricate relationships with each other and with their environment. The oceans of this ancient world were filled with an incredible diversity of single-celled organisms, each representing millions of years of evolutionary experimentation with different approaches to the fundamental challenges of life. How to capture energy, how to reproduce successfully, how to survive environmental changes, and how to compete effectively with other organisms for limited resources. But scattered among these familiar single-celled forms were the first representatives of something entirely new in the history of life on Earth. Organisms that had begun to explore the radical possibility that individual cells might be more successful, not as isolated competitors, but as cooperative partners in larger, more complex associations that could accomplish things that no single cell could achieve on its own. These were the first experiments in multicellularity, tentative collaborations between eukaryotic cells that would eventually give rise to every complex organism that has ever existed, from the smallest fungi and algae to the largest animals and plants, from the simplest sponges to the most sophisticated nervous systems capable of consciousness and contemplation. The transition from single-cell to multicellular life represents one of the most profound and mysterious transformations in the entire history of biology, a change so fundamental that it essentially created a new category of existence that operates according to different principles and possibilities than anything that had come before. What makes this transition so remarkable is not just that it happened, but how it happened through a gradual process of increasing cooperation and integration that eventually reached a point where the participating cells could no longer survive as independent organisms, having become so specialized and so interdependent that they constituted different parts of a larger biological whole. Imagine, if you will, floating in the warm, nutrient-rich waters of an ancient sea, perhaps in a shallow coastal lagoon, where currents moved slowly and conditions were stable enough to allow delicate biological experiments to persist and develop over long periods of time, and witnessing the first tentative steps toward multicellular organization as individual eukaryotic cells began to form temporary associations that lasted just long enough to provide some small advantage in the competition for survival and reproduction. These early collaborations probably lasted only hours or days before the participating cells separated and returned to their independent lives, but they represented the first exploration of possibilities that would eventually transform the entire character of life on Earth. Some of these early cellular associations may have formed when individual cells simply failed to separate completely after reproducing, remaining connected by thin bridges of cellular material that allowed them to share nutrients and coordinate their activities in simple ways. Others may have developed when cells that had been living in close proximity began to communicate with each other through chemical signals, gradually developing more sophisticated ways of coordinating their behavior and sharing information about environmental conditions or opportunities for feeding and reproduction. What made these early experiments in multicellularity successful was that the participating cells could accomplish things together that none of them could achieve alone, creating what scientists call emergent properties, capabilities that arise from the interaction between individual components but don't exist in any of the components by themselves. A simple example might be a group of cells that could capture food more efficiently by working together than any individual cell could manage on its own, or cells that could better survive environmental challenges by sharing resources and supporting each other through difficult periods. As these collaborative relationships became more successful and more beneficial to the participating cells, natural selection began to favor individuals that were better at cooperation, gradually leading to evolutionary changes that made multicellular associations more stable, more sophisticated, and more capable of complex coordinated activities. Over millions of years, what had started as temporary partnerships between independent cells evolved into permanent associations where the individual cells became increasingly specialized for different functions, creating the first hint of the division of labor that characterizes all complex multicellular organisms. Some cells in these early multicellular associations began to specialize in capturing food, developing enhanced abilities to detect and engulf prey or to absorb nutrients from the surrounding water, while other cells specialized in reproduction, maintaining the genetic material, and producing the next generation of multicellular organisms. Still others specialized in movement, developing sophisticated molecular machinery that could propel the entire multicellular organism through the water in search of food or favorable environmental conditions, or in protection, creating tough outer layers that could defend the more delicate internal cells from predators or environmental hazards. This division of labor was revolutionary because it allowed multicellular organisms to develop capabilities that would have been impossible for any single cell to achieve, no matter how sophisticated its internal organization might have been. A cell that specialized entirely in movement could develop much more effective locomotion systems than a cell that also had to maintain all the cellular machinery needed for feeding, reproduction, and other essential functions. While a cell that specialized in feeding could become far more efficient at capturing and processing food than a cell that was also responsible for movement and reproduction. The evolutionary advantages of this collaborative approach were so significant that multicellularity evolved independently many different times during the Proterozoic eon, giving rise to multiple lineages of complex organisms that explored different solutions to the fundamental challenges of multicellular life. Some of these early experiments in multicellularity led to the ancestors of modern plants, organisms that specialized in capturing energy from sunlight and became increasingly sophisticated at coordinating the activities of thousands or millions of individual cells in the service of photosynthetic productivity. Others led to the ancestors of fungi, organisms that specialized in breaking down complex organic materials and developed remarkable abilities to coordinate growth and reproduction across vast networks of interconnected cells. Still other experiments in multicellularity gave rise to the ancestors of animals, organisms that specialized in movement and feeding, and eventually developed the most sophisticated communication systems and coordination mechanisms that had ever existed in the history of life. These early animals were nothing like the complex creatures that we see in modern ecosystems, but rather simple collections of cells that had learned to work together in increasingly sophisticated ways, gradually developing the organizational principles that would eventually make possible the evolution of tissues, organs, organ systems, and all the remarkable diversity of animal life that would follow. Perhaps the most extraordinary aspect of these early experiments in multicellularity was the development of communication systems that allowed individual cells to coordinate their activities across the entire multicellular organism, creating the first biological equivalents of what we might recognize as information processing and decision-making systems. These weren't nervous systems as we understand them in modern animals, but rather simple chemical communication networks that allowed cells in different parts of the organism to share information about environmental conditions, coordinate their responses to challenges or opportunities, and maintain the integrated behavior that multicellular life requires. As multicellular organisms became larger and more complex, these communication systems became increasingly sophisticated, eventually developing the capacity to process information from the environment, store memories of past experiences, and make decisions about how to respond to new situations. The foundations were being laid for the evolution of nervous systems, brains, and eventually the kind of consciousness that makes contemplation and self-awareness possible. Though these developments were still hundreds of millions of years in the future, the world that was taking shape during this period of multicellular innovation was beginning to show the first signs of the biological complexity that we associate with modern ecosystems, though it was still profoundly different from anything that exists today. The oceans were filled with increasingly diverse communities of both single-celled and multicellular organisms, creating the first complex ecological relationships between different forms of life. Some multicellular organisms became predators that hunted single-celled prey, while others became filter feeders that captured microscopic organisms from the surrounding water, and still others became decomposers that broke down the remains of other organisms and recycled their nutrients back into the ecosystem. These ecological interactions created new evolutionary pressures that drove further innovation in both single-celled and multicellular organisms, leading to what scientists sometimes call an evolutionary arms race, where improvements in one type of organism create selective pressure for counter-improvements in other organisms, leading to increasingly sophisticated adaptations on all sides. Predators evolved better hunting strategies, which led to the evolution of better defensive mechanisms in their prey, which led to even more sophisticated hunting strategies, and so on, creating a feedback loop of innovation that continues to drive evolutionary change today. The development of these complex ecological relationships also began to have significant impacts on the global environment, as the metabolic activities of increasingly diverse and abundant multicellular organisms began to modify the chemistry of the oceans and atmosphere in new ways. Some multicellular organisms became very efficient at removing specific chemicals from seawater, while others produced waste products that had never existed before, gradually changing the chemical environment in ways that created new opportunities and challenges for all forms of life. Perhaps most importantly, the evolution of large, complex multicellular organisms began to create the first significant biological structures that were visible from space, as communities of organisms built reefs, forests of simple multicellular algae, and other biological formations that were large enough to begin affecting local and regional environmental conditions. These were the first ecosystems in the modern sense, integrated communities of organisms that were so interconnected and so influential that they essentially created their own environmental conditions, modifying temperature, chemistry, and nutrient availability in ways that supported the continued evolution and diversification of complex life. As we approach the end of this chapter in our journey through deep time, it's worth reflecting on the profound significance of the transition to multicellular life, because this development represents one of the most important thresholds in the entire history of our planet. The collaborative relationships that first emerged during the Proterozoic eon didn't just create new forms of microscopic life. They established the organizational principles that would eventually make possible every complex organism that has ever existed, including the remarkable biological systems that make human consciousness and culture possible. The multicellular organization that allows your body to function as an integrated whole, with specialized tissues and organs working together to maintain your health and enable your thoughts and experiences, reflects the same basic principles of cooperation and division of labor that first evolved in those ancient seas more than 1 billion years ago. The nervous system that makes consciousness possible is built upon communication mechanisms that have their roots in the simple chemical signaling systems that first allowed multicellular organisms to coordinate the activities of their component cells. The capacity for complex thought, emotion, and awareness that allows you to engage with these ideas represents the culmination of a process that began when individual cells first discovered that they could accomplish more together than they could achieve alone, that cooperation could create possibilities that no individual organism could access by itself, that the whole could indeed become greater than the sum of its parts through the magic of collaborative organization and shared purpose. In our next chapter, we'll explore how these early multicellular pioneers eventually gave rise to the first complex animals, organisms with sophisticated nervous systems and complex behaviors that would eventually lead to the great explosion of biological diversity that we call the Cambrian Revolution, when life finally developed the tools and capabilities needed to create the magnificent ecosystems that would eventually transform the entire surface of our planet. Until then, rest peacefully in the knowledge that you are yourself a miracle of multicellular cooperation, a community of trillions of cells working together so seamlessly and so effectively that they create the unified experience of consciousness and identity that you recognize as yourself, carrying forward the legacy of those ancient collaborative experiments that first discovered the extraordinary power of biological partnership and shared purpose. As we gather once more in this sacred space of quiet contemplation, where the boundaries between the ancient past and the eternal present seem to dissolve like shadows at dawn, I invite you to carry with you the profound wonder of our previous journey, where we witnessed those first tentative experiments in cellular cooperation that would eventually give rise to the magnificent complexity of multicellular life. Tonight, we approach one of the most mysterious and transformative periods in Earth's entire history, a time when life began to develop something that had never existed before in the 4 billion years since chemistry first learned to reproduce itself, the capacity to sense and respond to the world in ways that we might recognize as the first glimmers of awareness, the earliest stirrings of what would eventually become consciousness itself. We find ourselves now in the late Proterozoic eon, approximately 600 million years ago, in a world that was finally beginning to resemble something that we might recognize as familiar, though it was still profoundly alien in ways that stretched the imagination. The atmosphere had reached oxygen levels that were approaching those we breathe today, creating an environment that could support the kinds of active, energy-intensive lifestyles that complex animals would eventually require. The oceans were filled with diverse communities of both single-celled and multicellular organisms that had been refining their biological innovations for hundreds of millions of years, creating increasingly sophisticated ecosystems where cooperation and competition drove ever more remarkable evolutionary adaptations. But perhaps most importantly, the multicellular organisms that had been experimenting with cellular cooperation and division of labor for so long had finally reached a level of organizational complexity that made possible entirely new kinds of biological capabilities. Innovations so profound that they would fundamentally change the relationship between life and environment, between organism and world, between the biological and the physical, in ways that continue to shape our planet today. These were the first animals in the modern sense, organisms that had developed the capacity to move actively through their environment, to sense and respond to changes in their surroundings, and to process information about the world in ways that allowed them to make decisions and adapt their behavior to changing circumstances. The evolution of animals represents one of the most remarkable transitions in the history of life, a transformation that created entirely new categories of biological possibility and established organizational principles that would eventually make possible every form of complex behavior that we see in the living world today. From the simple responses of primitive nervous systems to the sophisticated cognitive abilities that allow humans to contemplate their own existence across vast spans of geological time. What makes this transition so extraordinary is not just that it happened, but how quickly it happened once the basic biological toolkit was in place, leading to what scientists call the Ediacaran explosion, when the first complex animals appeared almost simultaneously in oceans around the world. Imagine, if you will, floating in the warm, oxygen-rich waters of an ancient sea, perhaps above one of the soft sediment environments where many of these early animals made their homes, and witnessing the first tentative movements of organisms that were unlike anything that had ever existed before in Earth's history. These weren't the passive, stationary forms of life that had dominated the planet for billions of years, but rather active creatures that could propel themselves through the water, explore their environment, seek out food sources, and respond to threats or opportunities in ways that required unprecedented levels of coordination between different parts of their multicellular bodies. The first animals were probably quite simple by modern standards, lacking the sophisticated organ systems and complex behaviors that we associate with familiar creatures, but they possessed the fundamental innovations that define animal life: specialized tissues that could contract to produce movement, primitive nervous systems that could coordinate responses across the entire organism, and sensory structures that could detect changes in their environment and translate those changes into information that could guide behavior and decision-making. Perhaps the most revolutionary of these innovations was the development of nervous systems, networks of specialized cells that could transmit information rapidly across the entire organism, allowing different parts of the animal's body to communicate with each other and coordinate their activities in pursuit of common goals. These early nervous systems were nothing like the complex brains that would eventually evolve in more sophisticated animals, but rather simple networks of nerve cells that could carry signals from sensory structures to muscles, creating the basic input processing output systems that make animal behavior possible. The evolution of nervous systems represents one of the most profound developments in the history of life because it created the first biological information processing systems that could integrate multiple sources of environmental information, store memories of past experiences, and use that integrated information to guide adaptive responses to new situations. For the first time in Earth's history, there were organisms that could learn from experience, that could modify their behavior based on the outcomes of previous actions, that could begin to develop what we might recognize as primitive forms of decision-making and problem-solving. These early animals also developed the first sophisticated sensory systems, biological structures that could detect specific types of environmental information and convert that information into nerve signals that could be processed by the developing nervous systems. Some animals evolved light-sensitive cells that could detect the direction and intensity of sunlight, allowing them to navigate toward favorable environments or away from potential threats. Others developed chemical sensors that could detect food sources, predators, or potential mates by analyzing the molecular composition of the water around them. Still others evolved mechanical sensors that could detect vibrations, pressure changes, or physical contact, creating the foundation for the sense of touch that would eventually become one of the most important ways that animals interact with their physical environment. These sensory innovations were revolutionary because they allowed animals to gather information about their surroundings from a distance, to detect opportunities and threats before making direct contact with them, and to navigate through complex environments by integrating multiple sources of sensory information into coherent maps of their surroundings. The combination of nervous systems, sensory organs, and muscular systems created possibilities for animal behavior that were unlike anything that had existed before in the history of life. Early animals could now hunt actively for food. Rather than simply waiting for nutrients to come to them, they could flee from predators rather than simply enduring whatever environmental challenges they encountered. And they could seek out favorable environments rather than simply adapting to whatever conditions they found themselves in. These new capabilities had profound effects on the ecological relationships between different organisms, because active predators created new selective pressures for defensive adaptations in their prey, while mobile animals could exploit resources that had never been accessible to stationary organisms, leading to entirely new forms of ecological interaction and competition. The evolution of animals essentially created a new category of ecological relationship based on behavior rather than just chemistry, introducing elements of strategy, timing, and decision-making into ecological interactions for the first time in Earth's history. Some of the earliest animals to evolve were probably similar to modern jellyfish, simple creatures with radial symmetry and primitive nervous systems that could coordinate the movement of their bell-shaped bodies through the water, capturing small prey with stinging cells and digesting them in simple gut cavities. Others may have resembled modern sponges, though more active and responsive to their environment, filtering food from the water while using primitive muscular systems to adjust their body shape and position in response to changing conditions. But perhaps the most remarkable of these early animals were the first creatures to evolve bilateral symmetry, organisms with distinct front and back ends, left and right sides, and top and bottom surfaces, body plans that made possible much more sophisticated forms of movement and behavior than had been achievable with the radial symmetry of simpler animals. Bilateral animals could move in consistent directions, could develop specialized sensory organs at their front ends to gather information about where they were going, and could concentrate their nervous systems into centralized processing centers that would eventually evolve into the first primitive brains. The evolution of bilateral symmetry was particularly important because it established the basic body plan that would eventually give rise to most of the complex animals that we see in modern ecosystems. From simple worms to sophisticated vertebrates, all sharing the fundamental organizational principle of bilateral symmetry and the concentrated nervous systems that this body plan makes possible. The first bilateral animals were probably quite small and simple, perhaps resembling modern flatworms, but they possessed the basic architectural innovations that would eventually make possible the evolution of every complex animal that has ever existed. During this period, the ocean floor was becoming increasingly complex as these early animals began to modify their environment in ways that had never occurred before in Earth's history. Some animals learned to burrow into soft sediments, creating the first biological structures that extended below the surface of the seafloor and opening up entirely new ecological niches in the subsurface environment. Others built the first biological shelters and defensive structures, creating protective environments that could support more complex communities of organisms. These biological modifications of the physical environment were important because they created positive feedback loops between biological innovation and environmental complexity, where more complex environments supported more diverse communities of organisms, which in turn created even more complex environmental conditions, leading to an accelerating cycle of biological and ecological diversification that would eventually culminate in the explosive radiation of animal diversity that scientists call the Cambrian explosion. The late Proterozoic world was also experiencing significant geological and climatic changes that may have contributed to the conditions that made possible the evolution of complex animals. Ice ages came and went, creating periods of global cooling followed by warming phases that may have opened up new ecological opportunities for organisms that could adapt quickly to changing conditions. Volcanic activity continued to shape the continents and contribute nutrients to the oceans, while the gradual accumulation of oxygen in the atmosphere was reaching levels that could support the high metabolic demands of active animal lifestyles. Perhaps most importantly, the chemical environment of the oceans was finally becoming suitable for the kinds of complex biochemical processes that animal life requires. With oxygen levels high enough to support aerobic respiration, nutrient concentrations adequate to fuel rapid growth and reproduction, and chemical conditions stable enough to allow the development of sophisticated physiological systems that could maintain homeostasis in the face of environmental variability. As we approach the end of this chapter in our journey through deep time, it's worth reflecting on the profound significance of the innovations that we've been exploring together, because the evolution of animals represents one of the most important transitions in the entire history of our planet. The development of nervous systems, sensory organs, and coordinated behavior didn't just create new forms of life. It introduced entirely new categories of relationship between organisms and their environment, between different organisms, and ultimately, between life and consciousness, that would eventually make possible the kinds of awareness and contemplation that define human experience. The capacity for sensation, response, and primitive decision-making that first evolved during this period established the foundations for every form of animal behavior that would follow, from the simple reflexes of primitive nervous systems to the complex cognitive abilities that allow humans to create art, music, science, and philosophy. The bilateral body plan that first appeared in these ancient animals provided the architectural framework for every complex animal that has ever existed, including the remarkable biological systems that make human consciousness possible. The sensory innovations that allowed these early animals to detect and respond to their environment represent the distant ancestors of your own senses, the biological systems that allow you to see the beauty of the natural world, to hear the sounds of music and conversation, to feel the texture of objects and the warmth of sunlight, to taste and smell the richness of your environment, and to integrate all of these sensory experiences into the coherent awareness that you recognize as consciousness. In our next chapter, we'll explore how these early animal innovations eventually led to one of the most dramatic episodes of evolutionary creativity in Earth's history. The Cambrian explosion, when animal diversity exploded in a relatively short period of geological time, giving rise to most of the major animal groups that still exist today and establishing the foundations for all the complex ecosystems that would eventually transform the surface of our planet. Until then, rest peacefully in the knowledge that you carry within your own nervous system the direct legacy of those first animals that learned to sense and respond to their world, that the consciousness that allows you to contemplate these ancient mysteries is built upon biological innovations that first emerged in the warm seas of the late Proterozoic world, and that your capacity for awareness and understanding represents the continuation of a journey toward greater complexity and consciousness that began more than 500 million years ago. As we return once more to this gentle sanctuary of deep time, where the ancient stories of our planet unfold like dreams remembered across impossible distances of years and change, I invite you to rest for a moment in the quiet wonder of what we discovered in our last journey together, those first stirrings of sensation and awareness, when life learned to reach out into the world with primitive senses and respond with the first tentative movements guided by something approaching intention and choice. Tonight, we approach what many scientists consider to be the most spectacular and mysterious episode in the entire history of life on Earth. A period of such intense evolutionary creativity and innovation that it seems almost like a biological renaissance, when the toolkit of animal organization that had been slowly developing for millions of years suddenly exploded into an incredible diversity of forms and functions that would establish the basic patterns of complex life for all time to come. We find ourselves now at the beginning of the Phanerozoic Eon, approximately 540 million years ago, standing at the threshold of what geologists call the Cambrian period, named after the ancient Roman name for Wales, where some of the most spectacular fossils from this time were first discovered, embedded in rocks that had been waiting patiently for hundreds of millions of years to tell their remarkable story. The world that was taking shape at this moment in Earth's history was finally beginning to resemble something that we might recognize as familiar, with oxygen levels approaching modern concentrations, ocean chemistry that could support the kinds of complex physiological processes that active animal life requires, and environmental conditions that had achieved a stability and predictability that made possible the evolution of increasingly sophisticated forms of biological organization. But perhaps most importantly, the basic biological innovations that we explored in our previous chapters, the complex cellular architecture of eukaryotic cells, the cooperative relationships that made multicellular life possible, the nervous systems and sensory organs that allowed animals to sense and respond to their environment, had finally reached a level of sophistication and integration that made possible entirely new categories of biological possibility, innovations so profound and so diverse that they would fundamentally reshape the character of life on Earth in ways that continue to influence every ecosystem and every organism that exists today. The Cambrian explosion, as scientists have come to call this period of extraordinary evolutionary innovation, represents one of the most dramatic and puzzling episodes in the entire fossil record, a time when the diversity of animal life increased so rapidly and so dramatically that it seems almost incomprehensible when viewed against the much slower pace of evolutionary change that had characterized the previous billions of years of Earth's history. In the space of perhaps 20 or 30 million years, a brief moment in geological terms, though still an almost unimaginable span of time from a human perspective, life experimented with virtually every major form of animal organization that has ever existed, creating the basic body plans and biological innovations that would serve as the foundation for all complex ecosystems that would follow. Imagine, if you will, diving beneath the surface of one of those ancient Cambrian seas, perhaps in a shallow, warm lagoon where the water is crystal clear and the seafloor is carpeted with microbial mats that shimmer with the movement of countless tiny organisms, and finding yourself surrounded by a menagerie of creatures so strange and wonderful that they seem like the products of some cosmic imagination let loose to explore every possible variation on the theme of animal organization. Swimming through the water column above, you are jellyfish-like creatures with trailing tentacles and pulsing bells, some no larger than your fingernail, others the size of dinner plates, their translucent bodies catching and refracting the sunlight that filters down from the surface in patterns of ethereal beauty. Crawling across the seafloor beneath your feet are arthropods unlike anything that exists in modern oceans, creatures with multiple pairs of jointed legs, complex compound eyes that can detect the smallest movements in their environment, and armored exoskeletons that protect their soft internal organs while allowing for flexible, coordinated movement through the complex topography of the ancient seafloor. Some of these arthropods are predators, with grasping appendages and powerful mandibles that can crush the shells of their prey, while others are filter feeders with elaborate fans of feeding structures that constrain microscopic organisms from the surrounding water. Perhaps most remarkable of all are the creatures that seem to defy easy categorization, organisms that experimented with forms of biological organization that were so unusual that they have no modern equivalents, representing evolutionary experiments that explored possibilities for animal life that were ultimately not sustainable, but that demonstrate the incredible creativity and innovation that characterized this period of biological testing in history. There are creatures with five-fold symmetry, instead of the bilateral organization that would eventually dominate animal life, organisms with bizarre feeding structures that seem to operate according to principles that are completely different from anything seen in modern animals, and predators with grasping appendages and sensory organs arranged in patterns that seem almost alien in their complexity and sophistication. One of the most famous and spectacular of these Cambrian innovations was the evolution of sophisticated vision systems, biological technologies, for gathering and processing information about the environment that were far more advanced than anything that had existed before in the history of life. Some Cambrian arthropods developed compound eyes with thousands of individual lenses, each capable of detecting light, movement, and patterns of contrast in their environment, creating visual systems that could track the movement of prey or predators with remarkable precision and sensitivity. These early vision systems were revolutionary because they essentially created an information arms race between predators and prey, where the ability to see and be seen became crucial factors in survival and reproduction, driving the evolution of increasingly sophisticated camouflage strategies, defensive structures, and hunting behaviors that would eventually give rise to the complex ecological relationships that characterize modern ecosystems. For the first time in Earth's history, the shape, color, and movement patterns of organisms became important not just for their immediate physiological functions, but also for their effects on other organisms that might be watching them. The evolution of complex vision also made possible entirely new forms of animal behavior, including the ability to navigate across large distances by using visual landmarks, to recognize other members of the same species for mating purposes, and to coordinate group behaviors through visual communication systems that could transmit information rapidly across entire communities of organisms. The foundations were being laid for the kinds of complex social behaviors that would eventually evolve in more sophisticated animals, though these developments were still far in the future. But perhaps even more important than the evolution of individual innovations like sophisticated vision systems was the way that these various biological technologies began to be integrated into increasingly complex and capable animal designs, creating organisms that could combine multiple sensory systems, sophisticated nervous systems, and complex muscular and skeletal systems into coordinated packages that were far more capable than the sum of their individual parts. These integrated animal designs represented a new level of biological organization that had never existed before, creating the first organisms that we might recognize as genuinely similar to modern complex animals. The Cambrian seas were also witnessing the evolution of the first sophisticated predator-prey relationships, ecological interactions that were far more complex and dynamic than anything that had existed during the earlier periods of Earth's history, when most organisms were either filter feeders or simple grazers that fed on microbial mats and organic detritus. The evolution of active predators that could hunt and capture other animals created new selective pressures for defensive adaptations, leading to an evolutionary arms race that drove innovation in both offensive and defensive biological technologies. Some Cambrian animals evolved the first sophisticated armor systems, hard external shells, and protective structures that could resist the attacks of predators while still allowing for movement and feeding. Others developed escape strategies based on rapid movement, burrowing, or sophisticated camouflage that could make them nearly invisible against the complex backgrounds of the Cambrian seafloor. Still others evolved chemical defenses, producing toxic or unpalatable substances that could deter predators without requiring the energy investment needed for heavy armor or rapid escape responses. The predators themselves were evolving equally sophisticated hunting strategies, developing enhanced sensory systems that could detect prey from greater distances, more effective locomotion systems that could pursue escaping prey, and more powerful feeding structures that could overcome the defensive adaptations of their targets. Some Cambrian predators evolved the ability to break open armored shells, while others specialized in hunting fast-moving prey, and still others developed ambush strategies that relied on stealth and surprise rather than speed or strength. These predator-prey relationships were important not just because they drove the evolution of increasingly sophisticated individual organisms, but because they created the first complex food webs, ecological networks, where energy and nutrients flowed through multiple levels of biological organization, from primary producers that captured energy from sunlight or chemical sources, through various levels of consumers that fed on other organisms, to decomposers that broke down organic matter and recycled nutrients back into the ecosystem. The development of complex food webs was crucial for the long-term stability and productivity of Cambrian ecosystems, because it created multiple pathways for energy and nutrient flow, making these ecological communities more resilient to environmental changes and more capable of supporting high levels of biological diversity. The foundations were being laid for the kinds of complex ecosystems that would eventually support the incredible diversity of life that we see in modern oceans, forests, and other natural environments. During this same period, some Cambrian animals were beginning to experiment with the first hard shells and skeletal structures, biological innovations that would eventually become crucial for the preservation of fossils and our understanding of ancient life, but that were initially important for their protective and structural functions in living organisms. The evolution of hard shells represented a major innovation in biological materials science, as organisms learned to extract minerals from seawater and incorporate them into complex biological structures that could provide protection, support, and structural framework for increasingly large and complex body plans. The ability to build hard shells and skeletons also made possible the evolution of much larger animals than had been feasible during earlier periods, because these structural elements could support the mechanical stresses that are associated with increased body size while providing protection for the delicate internal organs that complex animal life requires. Some Cambrian animals grew to sizes that were unprecedented in the history of life, creating the first large marine ecosystems where organisms of different sizes and capabilities could coexist and interact in increasingly complex ways. The Cambrian explosion was also characterized by extensive experimentation with different approaches to fundamental biological problems like locomotion, feeding, reproduction, and environmental sensing, leading to the evolution of biological solutions that were often quite different from anything that exists in modern animals. Some Cambrian organisms developed forms of locomotion that combine swimming, crawling, and jet propulsion in ways that have no modern equivalents, while others evolved feeding strategies that seem almost impossibly complex when compared to the simpler approaches used by most modern animals. This period of biological experimentation was possible because the Cambrian world was relatively free from the kinds of competitive pressures that would eventually eliminate many of these unusual biological innovations, creating a kind of evolutionary playground where life could explore possibilities that would later prove to be evolutionary dead ends, but that demonstrate the incredible creative potential that exists within biological systems when environmental conditions permit extensive experimentation and innovation. As we approach the end of this chapter in our journey through deep time, it's worth reflecting on the profound significance of the Cambrian explosion for our understanding of life's potential for creativity and innovation, because this period represents one of the most dramatic demonstrations in Earth's history of the capacity for biological systems to generate entirely new forms of organization and capability when the right conditions are present. The innovations that emerged during the Cambrian period didn't just create new forms of individual organisms. They established the basic organizational principles and biological technologies that would serve as the foundation for all complex life that would follow. The nervous systems that make human consciousness possible trace their ancestry directly back to the information processing, innovations that first appeared during the Cambrian explosion, while the sensory organs that allow you to perceive and interact with your environment represent refinements and elaborations of biological technologies that were first developed by Cambrian animals, exploring the possibilities of vision, hearing, touch, and chemical sensation. The complex ecosystems that support the rich diversity of life on modern Earth are built upon ecological principles and relationships that were first established during this remarkable period of biological innovation. Perhaps most importantly, the Cambrian explosion demonstrates that life's capacity for creativity and innovation is virtually limitless when environmental conditions permit extensive experimentation and when the basic biological toolkit has reached sufficient sophistication to support rapid evolutionary change. The incredible diversity of forms and functions that emerged during this period reminds us that the living world is far more creative and inventive than we might imagine, capable of solutions to biological problems that often exceed anything that human imagination might conceive. In our final chapter, we'll explore how the innovations of the Cambrian explosion eventually led to the colonization of land and the evolution of terrestrial ecosystems, completing the transformation of Earth from a largely aquatic planet to the rich, diverse world of land and sea that we know today, and setting the stage for all the remarkable developments in the history of life that would eventually lead to the emergence of consciousness, culture, and our own capacity to contemplate and appreciate the magnificent story that we've been exploring together. Until then, rest peacefully in the knowledge that you are part of a continuous chain of biological innovation and creativity that stretches back through the Cambrian explosion to the very dawn of complex life, and that the capacity for wonder and understanding that allows you to appreciate these ancient mysteries represents the culmination of more than 500 million years of evolution toward greater complexity, awareness, and consciousness. As we gather for the final time in this sacred space of contemplation and wonder, where we have traveled together through nearly 4.5 billion years of Earth's magnificent transformation, from a molten ball of rock to a world capable of supporting not only life, but consciousness itself, I invite you to rest for a moment in the profound beauty of all that we have witnessed together. The slow cooling of our planet under alien skies, the first stirrings of chemistry learning to reproduce itself, the emergence of cells and the development of cooperation between organisms, the evolution of sensation and awareness, and the spectacular flowering of animal diversity that filled the ancient oceans with forms of life so remarkable that they still inspire wonder and amazement today. Tonight, in this final chapter of our journey through deep time, we witness the completion of one of the most important transitions in the entire history of our planet. The moment when life finally learned to leave the protective embrace of the ocean and venture onto the harsh, exposed surfaces of the continents, beginning the transformation of Earth's landmasses from sterile, rocky wastelands into the rich, green, living landscapes that would eventually become home to forests and grasslands, rivers and lakes, and all the magnificent terrestrial ecosystems that we know and love today. This is the story of how life conquered land, how organisms that had evolved for hundreds of millions of years in the buoyant, chemically stable environment of the sea learned to survive in the challenging world of gravity, weather, and seasonal change that characterizes life on land. We find ourselves now in the Middle Paleozoic era, approximately 400 million years ago, in a world where the innovations of the Cambrian explosion had been refined and elaborated for more than 100 million years, creating increasingly sophisticated marine ecosystems filled with creatures that would be recognizable to us as ancestors of modern fish, arthropods, mollusks, and many other familiar groups of animals. The oceans were rich with life, from microscopic plankton that formed the base of complex food webs to large predators that roamed the open seas, and the coastal waters were filled with reefs built by corals and other organisms that created complex three-dimensional habitats supporting incredible diversity of marine life. But above the surface of these life-filled seas, the continents remained largely barren, vast expanses of naked rock and sediment that were scoured by wind and rain but showed little sign of the biological processes that were transforming the underwater world below. The atmosphere was rich with oxygen and water vapor, creating weather patterns and climate systems that were increasingly similar to those we know today, but the land itself remained largely uninhabitable, lacking the soil, shelter, and food resources that complex life requires. The colonization of land represents one of the most challenging transitions that life has ever accomplished, because terrestrial environments pose biological problems that simply don't exist in aquatic habitats, problems that required entirely new biological solutions and innovations that pushed the boundaries of what living organisms could achieve. In the ocean, organisms are supported by the buoyancy of water, protected from harmful radiation by the water column above them, and surrounded by a relatively stable chemical environment where nutrients and dissolved gases are readily available. On land, organisms must support their own weight against gravity, protect themselves from intense solar radiation and extreme temperature variations, and obtain water and nutrients from sources that are often scarce and widely distributed. The first pioneers to make the transition from water to land were probably simple plants, organisms that had evolved from aquatic algae and had developed the biological innovations needed to survive in terrestrial environments, while still remaining close enough to water sources to meet their basic physiological needs. These early land plants were nothing like the complex trees and flowers that we associate with modern terrestrial vegetation, but rather simple, low-growing organisms that resembled modern mosses and liverworts, lacking the sophisticated vascular systems and structural supports that would eventually make possible the evolution of larger, more complex plant communities. But even these simple early land plants represented remarkable innovations in biological engineering, because they had solved fundamental problems that had never been encountered by aquatic organisms. They had evolved waxy coatings that could prevent water loss in the dry air, root-like structures that could extract water and nutrients from soil and sediment, and reproductive systems that could function in the absence of the water currents that aquatic plants depend on for dispersing their offspring. Perhaps most importantly, these early land plants had developed the ability to synthesize lignin, a complex organic polymer that could provide structural support in the absence of water's buoyancy, allowing plants to grow upward toward the light while maintaining the mechanical strength needed to resist wind and weather. The evolution of lignin was crucial for the eventual development of forests and other complex plant communities, because it made possible the evolution of woody stems and trunks that could support large, complex plant bodies that could compete effectively for access to sunlight. As these pioneer plants became established in terrestrial environments, they began to transform the physical and chemical characteristics of the land surface in ways that made it increasingly hospitable for other forms of life. Plant roots broke down rock and mineral surfaces, creating the first soils and contributing organic matter that could support microbial communities and provide nutrients for other organisms. The decaying remains of plants added organic carbon to terrestrial environments, creating chemical resources that had never existed on land before, and establishing the foundation for terrestrial food webs. The presence of plant communities on land also began to modify local climate and weather patterns, as vegetation could retain moisture, moderate temperature extremes, and create sheltered microenvironments that were more hospitable for animal life than the exposed rock surfaces that had previously characterized terrestrial environments. For the first time in Earth's history, the continents were beginning to show patches of green when viewed from space, marking the beginning of the transformation that would eventually cover most of the land surface with living ecosystems. The success of early land plants created opportunities for animal life to follow them onto the continents, but this transition required its own set of biological innovations and adaptations that were just as challenging as those that plants had needed to develop. Animals face additional problems on land because they must be able to move around to find food and mates, which means they need more sophisticated structural support systems than plants, and they must be able to extract oxygen from air rather than water, which requires entirely different respiratory systems than those that work in aquatic environments. The first animals to successfully colonize terrestrial environments were probably arthropods, creatures that had already evolved sophisticated exoskeletons in marine environments, and that could adapt these structural systems to provide the support needed for movement on land. These early terrestrial arthropods were likely similar to modern millipedes and centipedes, creatures that could move through the leaf litter and soil of early plant communities while feeding on decomposing plant material and smaller organisms. The evolution of terrestrial arthropods was significant because it established the first complex food webs on land, creating ecological relationships between plants, decomposer organisms, and the predators that fed on them. These early terrestrial ecosystems were still quite simple compared to modern forest communities, but they represented the beginning of the complex ecological networks that would eventually support the incredible diversity of terrestrial life that we see today. But perhaps the most dramatic innovation in the colonization of land was the evolution of vertebrates that could survive and thrive in terrestrial environments, a transition that required fundamental changes in respiratory systems, circulatory systems, skeletal systems, and reproductive systems that were so extensive they essentially created entirely new categories of animal organization. The first vertebrates to make this transition were the ancestors of modern amphibians, creatures that evolved from lobe-finned fish that had already developed some of the features needed for terrestrial life, including primitive lungs that could extract oxygen from air and muscular fins that could support limited movement on land. The evolution of terrestrial vertebrates was revolutionary because it created the foundation for all the complex animal life that would eventually characterize terrestrial ecosystems, from reptiles and mammals to birds and all the other vertebrate groups that dominate modern land environments. These early terrestrial vertebrates were still closely tied to aquatic environments for reproduction and moisture, but they had solved the basic engineering problems that make terrestrial animal life possible, and had established the biological innovations that would eventually allow vertebrates to become completely independent of aquatic environments. As plant and animal communities became established on land, they began to interact with geological and climatic processes in ways that further transformed the character of terrestrial environments. Plant roots and microbial communities accelerated the weathering of rocks and the formation of soils, while the organic matter produced by terrestrial ecosystems began to influence the chemistry of rivers and lakes, and even the composition of the atmosphere itself. The presence of extensive forests began to affect regional and global climate patterns, as vegetation could influence rainfall patterns, moderate temperature extremes, and affect the reflection and absorption of solar radiation by the land surface. The evolution of terrestrial ecosystems essentially created new feedback loops between the biological and physical systems of our planet, feedback loops that continue to influence Earth's climate and environment today. Perhaps most importantly, the colonization of land completed the transformation of Earth from a planet where life was confined to the oceans to a world where biological processes operated across the entire surface of the planet, creating the integrated global ecosystem that we call the biosphere. For the first time in Earth's history, living processes were active in every major environment on the planet's surface, from the deepest ocean trenches to the highest mountain peaks, creating a level of biological integration and complexity that had never existed before. The success of terrestrial life also set the stage for even more dramatic evolutionary innovations that would eventually lead to the evolution of complex nervous systems, sophisticated sensory organs, and ultimately the emergence of consciousness and intelligence in various lineages of terrestrial animals. The challenging environments and complex ecological relationships that characterize terrestrial ecosystems created selective pressures for increasingly sophisticated behavioral and cognitive abilities, leading eventually to the evolution of the kinds of complex brains that make human consciousness and culture possible. As we reach the end of our journey through deep time, standing now at the threshold of the world that we recognize as our own, it's worth reflecting on the extraordinary story that we've witnessed together, because the transformation of Earth from a lifeless ball of rock to a living, breathing planet capable of supporting consciousness and contemplation represents one of the most remarkable achievements in the history of the universe. Every step in this incredible journey, from the first stirrings of chemistry learning to reproduce itself to the colonization of land by complex multicellular organisms, has contributed to creating the conditions that make our own existence possible. The oxygen that sustains your life tonight was produced by countless generations of photosynthetic organisms over billions of years. The complex cellular machinery that powers your thoughts and dreams represents the culmination of evolutionary innovations that began with the first protocells forming around hydrothermal vents in ancient oceans. The sensory systems that allow you to perceive and appreciate the beauty of the natural world trace their ancestry to the first animals that developed nervous systems and learned to sense and respond to their environment. The very capacity for consciousness and contemplation that allows you to engage with these ideas represents the continuation of a journey toward greater complexity and awareness that began more than 4 billion years ago, when chemistry first learned to preserve and reproduce patterns of organization across time. You are not separate from this ancient story. You are part of it. The current chapter, in an ongoing narrative of increasing complexity, creativity, and consciousness that stretches back to the very origins of our planet. As you rest tonight, knowing that our journey together through deep time has reached its conclusion, carry with you the profound understanding that you are connected across vast spans of geological time to every innovation, every adaptation, every breakthrough that we have witnessed together. The same creative forces that built the first cells, that developed photosynthesis, that created the first animals with nervous systems, that colonized the land and filled it with life, continue to operate through you and through every living thing on our planet. You are made of star stuff, forged in the hearts of ancient supernovas, cooled and condensed in the solar nebula that gave birth to our solar system, organized by billions of years of evolution into the remarkable biological systems that make consciousness and contemplation possible. You are, in the most literal sense, the universe becoming aware of itself, the culmination of 4.5 billion years of planetary evolution, the current expression of Earth's ongoing experiment in complexity and consciousness. The story we have told together is not just the story of ancient Earth. It is your story, the story of how you came to be, the story of how consciousness arose from chemistry, how awareness emerged from matter, how the capacity for wonder and understanding developed from the simple imperative of molecules to preserve and reproduce their patterns across time. Rest peacefully in this knowledge, and know that you carry within yourself the legacy of every innovation, every breakthrough, every moment of creativity that has shaped the history of life on our remarkable planet. Sweet dreams, fellow travelers, and thank you for joining me on this incredible journey through the deep history of our world. May you always remember that you are part of something far greater and more magnificent than you might have imagined, connected through unbroken chains of inheritance and causation to the very origins of complexity and consciousness in our universe. The story continues through you, and the next chapters in Earth's great adventure are yet to be written.